You know, numbers are absolutely everywhere. We see them on food labels, in the news, on our car dashboards. But think about it. On their own, they're just symbols. Today, we are going to pull back the curtain and uncover the hidden language that actually gives numbers all their power. All right, let's get into it. So, I want to start with a really simple question. Just look at this number on the screen, 100. Is that a lot? Is it a little? Maybe a good score on a test? Or a bad one? The truth is, without any other information, we have absolutely no idea what it means. It's just floating there. And believe me, this isn't just some philosophical puzzle. Let's imagine a doctor prescribes the anticonvulsant phenobarbital. Now, a dose of 100 could mean 100 milligrams, which is a totally safe therapeutic amount. But what if someone misread that as 100 grams? Well, that is more than 10 times the lethal dose. The stakes here are incredibly, incredibly high. And that right there gets to the heart of the problem. A number all by itself is basically just noise. It has no context, and as we just saw, that kind of ambiguity can be really, really dangerous. To make any sense of the world, we need some kind of standard to compare things to. So what's really fascinating is that any proper measurement actually has three parts to it. First, you've got the number itself, the magnitude. Then you have the unit, and this is our crucial standard of comparison. And finally, there's always a level of uncertainty, which kind of hints at how precise the measurement really is. I mean, this quote just says it all, doesn't it? The unit is the anchor that gives a number its meaning. Without it, we're just completely lost in this sea of confusing and sometimes really harmful data. So, how did science fix this mess? Well, the solution was brilliant in its simplicity. We needed to create a universal language, a single, globally agreed-upon system that would let scientists, doctors, engineers, honestly everyone, communicate clearly with zero ambiguity no matter where they were in the world. And that solution is the International System of Units, or as pretty much everyone calls it, SI units. It was adopted across the globe back in 1964, and it's basically the modern metric system. It provides the rock-solid foundation for all scientific measurement. It's just such an elegant answer to all that chaos we were talking about. Probably the best way to think about the SI system is to see it as an alphabet. It only has 7 fundamental base units, but with them, you can describe pretty much anything and everything in the known universe. You've got the meter for length, the kilogram for mass, the second for time, and 4 others. These are the absolute fundamental building blocks. Okay, so if the base units are our new alphabet, then prefixes are what give this language its incredible, mind-boggling range. They let us talk about things as vast as the distance between galaxies and as tiny as a single atom, all while using the exact same system. Let's just take the meter, for example. If you add the prefix kilo, you get a kilometer, which is just 1,000 meters. Simple. But if you add the prefix milli, you get a millimeter, which is just 1,000th of a meter. See? One simple base unit, 2 little prefixes, and suddenly we can describe both the length of a long road trip and the thickness of your fingernail. And here are some of the most common prefixes you'll see. The really brilliant thing about this whole system is that it's all based on powers of 10. Kilo is 1,000, centi is 100th, milli is 1,000th, and it just goes on from there. It's so logical, so consistent, and it makes scaling up or down incredibly easy. Now imagine you're an engineer at a power company and you have to write down this number all day long. It's huge, it's clunky, and it would be so easy to accidentally add or drop a zero, which would be a massive mistake. There's just gotta be a better way, right? Of course there is. Using an SI prefix, that enormous, clunky number becomes a simple, elegant 5 terawatts. That's it. The prefix tera just stands in for 10 to the power of 12. This is such a perfect example of how these prefixes clean everything up and make our lives so much easier. Okay, so we have our alphabet, those 7 base units, and we have our amazing scaling tool, the prefixes. So now we can actually start combining these building blocks to describe even more complex ideas. Yeah, when we combine base units, we create something called derived units. So if base units are the letters, then you can think of derived units as the words. And these words allow us to measure all sorts of new concepts, like area, speed, volume, and density. Let's actually see how this works by building the unit for volume right from scratch. We start with our base unit for length, the meter, which is really just a line in one dimension. Now, if we expand that line into a square, we get area, which we measure in square meters. And then, if we take that square and pull it out into a cube, we get volume, measured in cubic meters. And just like that, we've built a brand new unit from our original alphabet. Now, the cubic meter is the official SI unit, but for everyday stuff, we often use more convenient derived units. You've definitely heard of the liter, which is nothing more than a cubic decimeter. And a milliliter? That's just a cubic centimeter. See? They're all directly connected back to that fundamental base unit of length, the meter. Okay, this is where it gets really, really cool. We can now use these new tools, these derived units, to do some detective work, to uncover the hidden properties of matter. And our secret weapon for this is going to be density. So let's look at a classic scenario. For centuries, right, scammers have tried to pass off cheaper metals as solid gold. A really common trick was to take a gold brick, hollow it out, and fill it with lead. They look and even feel pretty similar. So how on earth could you tell the difference without actually cutting it open? The answer, my friends, is density. Density is a derived unit that you get by dividing an object's mass by its volume. And here's the crucial part. Every pure substance, whether it's gold or lead or water, has its own unique characteristic density. It's like a physical fingerprint. Let's just run the numbers on a cube of lead. Say we put it on a scale and find its mass is 90.7 grams. Then we measure its sides to calculate its volume, and that comes out to 8.00 cubic centimeters. Okay, now we just divide the mass by the volume and we get a density of 11.3 grams per cubic centimeter. And now, for the moment of truth, we compare the density we just calculated to the known density of pure gold. The density of gold is 19.3 grams per cubic centimeter. Our cube is only 11.3. They are not even close. And just like that, the scam is busted. We didn't have to damage the brick. We didn't need any fancy, expensive equipment. All we needed were 2 simple measurements and 1 derived unit to reveal the hidden truth. The numbers, when you use them correctly, do not lie. So we've gone on this journey from a simple, meaningless number all the way to a system that can uncover fraud and identify the very essence of matter. Which really just leaves us with one final thought. If a simple measurement can reveal a material's true identity, what other invisible truths about our world can measurement help us see?